Hello, everyone, and thank you for joining today's webinar, 7 Little-Known Habits of the Most Successful Variation Analysis Modeling Engineers. Please note that you have joined as an audience member and are muted. My name is Madeline, and I'm today's moderator, and we're going to go ahead and get started with a quick overview of our agenda. We'll begin with a little bit about geometric solutions, who we are, and how we can help you. And then we'll jump into our main topic, variation analysis. Specifically, these 7 little-known habits directly from our expert, Curtis. Our presenter today is Curtis, Director of Technology at Geometric Solutions. Curtis has more than 30 years of experience in manufacturing technology and has been at the forefront of digital simulation, specifically related to virtual prototyping and dimensional quality. He is recognized internationally as an expert in digital simulation using 3D tolerance analysis tools, and for the most part, he's used all the major CADs, PDMs, CAE systems, and multiple digital simulation applications. As you will see, Curtis enjoys the blending of new technology, software, and best-in-class processes, all while driving the need for quality, resulting in the reduction of overall costs. Now for a quick intro into who we are at Geometric Solutions. We are part of the Waltonen family that is made up of 3 companies located throughout the Midwest: Waltonen Engineering, Independence Tooling, and Geometric Solutions. Our story is pretty simple. Waltonen develops innovative engineering solutions using Siemens software. We got so good at it, Geometric Solutions started selling the same potential for success in the form of Siemens software. So when it comes to implementing and optimizing these solutions like an expert, Geometric Solutions can get you there. And then there's really no better way to say what we do at Geometric Solutions than what our president and owner, Lloyd Brown, said. Our ability to successfully partner with our customers comes from our experience using the tools we sell every day. Like I said, if you want to learn how to be a super user of these programs, come to us because we're already doing it every day. And now I'm going to pass things off to Curtis. Curtis, take it away.
VSA, or variation analysis, is a tool that is not, widely used by a lot of companies, and then the experts are far and few between. I'm going to pick on something like NX. NX is a great tool. A lot of companies have hundreds of seats of those, but for those 100 seats, they might have 1 or 2 of VSA, and the expertise isn't always out there. So these are some little helpful tidbits to make you a little more successful in using the tool. So what are the 7 habits we're going to go through today? One of the things we're going to talk about is start files and how to start models quickly and efficiently, and the value of having start files. How to organize your model, naming conventions, using the math equation function, and we'll talk about why we want to use that. Multiple cut and paste and how to be successful at it and things you can do. Not everybody knows everything about that. Conditional logic. Inside the assembly routines, there's these conditional logics that we can change things on and off and pick which routines are being used. And then how to do checking. And we're going to really focus on checking around assembly logic, because we found that most errors that we come across are in that arena. So let's get to it. So let's talk about start files. So what the start files do is keep your predefined standards and preferences from model to model. That's what we're trying to use it for. CAD guys have used it for years because they always start out with the same size drawing with the same title block and such. What we want to do is do that for VSA. So I can actually control the colors of my features, the contents of my tables that show up, some simulation settings, background, and the blue background here, performance settings. So we want to set all those up, save that, and that way we don't have to redefine it every time we start. When we go File, New Model, it will start it to the default configuration that Siemens has prepared it, not necessarily how you and your team want to use it. So let's take a look at this. So here I am, I'm going to start up a new file. So I'm going to start a new process document, and inside that process document, we're going to default to millimeters. I usually make 2 of these files, one in inches and one in millimeters. So here I have a blank process. What I want to do is go into my preferences. So in my preferences here, the first thing I do is, or we do as a team, is change the color of all our features. Everybody, who doesn't have blue parts for all their parts in their assembly. So instead of using the default blue that comes out of the box from Siemens software, we change it to common part. That way, if I have a green part, it comes up green. If I have an orange part, it comes up orange. It matches the color of the part, makes it much easier to see and debug. The points we don't change. We like that nice green sharp point. Naming conventions, you can actually do special naming instead of defaulting it to hole and slot. You can actually have other custom names in there. I like removing the end caps from our pins. So our pins don't look like pins, they look like circles, but we change it every now and then. If I use measurement data, we don't have DPV installed at our site here, so we use XML to import our data in. Automatic backup, this is a great thing, how frequent you want to do it. Just remember, if you got large models, it slows you down. It stops and does the backup while you're working. I don't like showing the name of the feature. I just like to see the feature. I like to see it. But you can see the name, and it's just defaults we like. We don't like seeing measurement operations because if we have a large model with a bunch of measurement operations, it looks like a porcupine. If I'm starting a model up, I'm not doing a lot of simulations. I'm doing debug. I just want 100. So this is how we want to start, and I want to see them, especially if I'm starting. I want to see those Monte Carlo simulations. Results. We're doing millimeters. Not often working in the micron level. Most of the time, 2 millimeters is great. It's a starting point. We like to show a title on every one of our reports. So if we write the name of our, in this case, this demo model, it puts it in there. We like to change what our table defaults show up. Nominal, mean, estimated low and high, and range. Those are the important values. A lot of times we want the estimated values of parts out of spec. So we want to put that in there. So we define all those things. We want to save that. In addition, there's a few other things we want to save. So here we have our preferences for our background and everything. So what I want to do is we like to have it vertical, and you can pick whatever colors you like. This sometimes is more of a personal preference than anything else. I like this nice shade of blue. I'm going to go a little darker on top, and on the bottom, I'm just going to pick that base color of blue, and I'm going to create a nice two-tone background screen, and there we go. That makes it nice and easy. Performance. We use part investigation 100% of the time when we're doing variation analysis. The reasoning is, some people may have seen this happen, but when they start modeling points, and I'm just going to add a point here real quick. So when you start modeling points, you want to be able to see it on the screen. So I can actually see that dot. That's where my point is, so I can see it. If I go to my performance and I go anything other than part investigation, I don't see it on the screen. So this is a Viz mockup setting that allows me to see the point or not. So if you ever have problems where you don't see the point, this is it. So here I want to save this. So I'm just going to go to a starting point here, and I'm just going to come up here in this demo area, and I'm just going to write a name for a model, and I'm just going to call it here my start model, and I'm just going to put millimeters. This is a millimeter model. Every time I start a file, every new project, I have a standard directory that has a naming convention with a folder for CAD files, a folder for drawings, a folder for the PDOs. I put this in my folder for my PDO, rename it to the name I'm going to name it for that model, and then the start model starts me off exactly the way I want to go. So it just saves times, and it's less frustrating than starting a model and creating everything in blue features and then coming back and changing back the colors. So let's talk about the next thing. Organization of your model. How to organize this so it's readable and makes sense to follow, right? I mean, I've seen models like this on the right where all the parts are done first, there's an assembly in there. The assembly operations are secondary. We're not sure which assembly operations go to what parts. Later on, they added a part number 6 in there. Then they added some more assembly operations while that assembling part 6 or something above it. What's going on inside the sub-assembly? It's not really clear how this is. So there's ways to actually organize your model to make it a little more clear to read and understandable. So let's take a look at this. This is an existing model that we have. This is a automatic shifter for a car. Mounts to a cockpit instead of the floor. So if I do the simulation here, you can see the shifter moving into place when it goes to its nominal simulation. You want to go back. So you can see it's pivoting off that pin and it's pulling out this cable, and that's what we want to check. But for naming conventions, adapter plate, that's our base thing. It's the first thing. It's everything is getting mounted to that. This part, this little pivot point down here on the bottom in yellow, that is being mounted directly to that. Then I have a base pin. That base pin is going inside here. So I have my target, and then I start adding my objects one by one in sequence. Here I have an assembly. So inside the assembly, I have individual parts that are in there. So let's just look at the highest level. I have an adapter plate. I have this pivot point going on there. And then I have the assembly routine to assemble the pivot point, the base pin and the base routine, the pin, the routine to assemble that. And then at the assembly level, the core assembly grouping is there, and then the routine to assemble it is immediately after. So I know what routines are doing what. Inside that core assembly, let's take a look at that. I happen to have just a few parts, but the first part in there is the base part, and then I put the pivot pin into it. So the core is there, then the pivot pin, then the assembly routine to do that. Then this quiet cap, and then the routine to assemble it is there. The switch, then the routine. Very logical and order. Anybody in our organization that reads these models knows how to see it and understand it. And I know what's inside the assembly, and it's being assembled inside the assembly. And then I know how the assembly itself is being mounted to its piece. So you can see it piece by piece, how it's going together, very logically, target, object, assembly routine, in that order. Once I start looking at a single part, what we want to do is kind of like put primary datum. So you notice they're listed up front. But then we do groupings here. So we have this adapter plate, and it's a node and a switch here, that has part or features inside it. It's just a way to organize this. So here, let's turn these other parts off. But you can see here for where the switches, when I start standing on these pieces, this is the hole. You can see it in yellow there, the slot, then the mating plane. So this little grouping is all around the switches, and it makes it very convenient to read through this model, especially when I have a grouping like this. Here I got 15 or so features, and if all of these expand out, it'll fill up the whole page here on the left. So these little subgrouping just make it quicker and easy to read, debug, and share with your team. And the way we do that is we just go to the top of that part, say add a group node, and then we can put those features inside it. Makes it very easy to read, very easy to understand. And, even here down below, I have multiple assembly routines for shifting this thing through the different positions from drive to park to reverse. And we even have these labels here that define those. So nice clear-cut labels. Those labels are fixtures with nothing in them. Those dashes going across here give me a nice line, and they're just arbitrary items there. We group measurements, so we see things in logical chunks. It makes it so much quicker and easy to read and to debug. And 6 months from now, if you go to work on the same model again, you can actually figure it out because it's very logical and organized. So we talked about how to organize it, but now we want to talk about naming conventions, and they're kind of interrelated. So let's look at how that makes a difference. If I see a model like this one on the right, just as part 1, part 2, part 3, it takes the default part naming constructions that variation analysis gives you, but they should be named to match what makes sense with your model, right? The same thing with the assembly operations and the measurements. We want to make sure they're very cleanly named so we understand what's going on. So let's take a look at this. So here we happen to have a model, and we got the adapter plate, the pivot pin, the base pin. They're actually names of the parts that are in the assembly. So anybody looking at this knows what it is. If you notice here, we have these little --0 or arrow here. That is all my assembly routines. Whenever I see that, I know it's an assembly routine. Datums, we actually say datums, and you notice this at. The at is saying what it's mating to, or what, where it is on the assembly. You know, we're really big about these ats. Like here, at the adapter plate, this is every area in this group node that mates up with the adapter plate. You know, everything in this switch, everything in this spring is in that group. So let's take a look at this switch. Expand this out. Mating plane at switch datum A. Datum D hole, slot, at. And what we do is we give the mating feature on the mating part. So we know the datum D on this part matches with datum B on the switch. The slot matches with datum C on the switch. So it's very convenient. Where that really makes a difference is when you start looking at your HLM results, your designed experiments. It's telling you who contributed what. It makes it very readable. All right. There we have part names. Sometimes we got, you know, part numbers and such. So here we have a fixture for this part. So that part is one big assembly. Inside there, I have a fixture for that that takes this assembly of the upper rails and some other parts and puts them in there. So they're just named to match the part numbers, because some companies go by part numbers, some people go by names. You know, inside here, I have a fixture for that upper rail assembly that includes these two parts and that floor pan assembly, and so on and so on. As we just go through it, it's very logical, it's very clean, and if your company uses that type of logic, this makes perfect sense. So here we're measuring. So we want the ABC, you know, to the ABC datums, these different areas that we're measuring. And you notice there's numbering there to make sense. But then we have an assembly where we're going to assemble it on datums D, E, and F and measure to D, E, and F. So, you know, very clean, simple naming methods makes it so much easier to root cause and to check things out. One of the practices we do as a company is we don't let a model go out without not having another VSA person check it. For that person to check it, this makes his life so much easier, or her life, because it is well organized and clearly understood. The extra time it takes to do it now will save you tons of time later. So, question we have for people that have been doing modeling. Have you ever been confused reading your model that you created 6 months ago and you're going back into it to do an update?
Looks like our top answer is yes, have to dig through it for hours to remember.
Yep, that's quite common. You know, until we started standardizing on naming conventions and such, it took a long time to do that, you know. And I've even talked to folks that have kind of recreated stuff because they couldn't figure out the mess that they had, and it was simpler to recreate than to do it from scratch. You know, to try to fix what they had or update what they had. So it's kind of scary, but it's the common practice. So if you organize it well and name things well, it makes life so much easier when you go back into your old model or you hand it off to one of your coworkers to work on. So let's move on to the next slide. Come on, there we go. Math equations. This is something that we use quite frequently, and we don't see a lot of use of it out there in the field from people we've talked to. So let's talk about why we care about it and what we do. What math equation is a custom measurement type. We're going to talk about, you know, how to use it and how it works, but specifically, it allows us to convert measurement data, which is typically measurement between a couple of things, into another format that I can report that typically meets the requirement that is stated that we're trying to meet. So let's talk about this. So here I have a simple assembly. It's really a couple of plates and a screw going through it. And so real simple assembly. And what we're worried about is thread engagement depth. Our company, you know, so here we got a base, a plate, and a bolt. Based on the thickness of that top plate and the length of the bolt, will I have enough engagement of threads to make sure I'm meeting my company standard? I don't want it too long because it's extra weight, it's extra cost. So I want to right size this. And if we look at the pitch diameter here in yellow, that's a little smaller. So it's a 6 millimeter bolt. The pitch diameter is 5.35. I just happen to know that. And what we care about is where the last thread is. So we got a plane down here representing the last thread with a point on it. And what we want to do is measure from basically the plane that is the top of that blue surface. And so there's the point in that plane. We're just trying to measure it. And we want to specify limits. Nominally it's 8.3. Our lower spec is 8.025, right? How did I get that? It's a 5.3 pitch diameter times 1.5, which is our minimum engagement requirement at our company, and it equal to 8.025. So that's how I calculated that. So I can report this way, which is great. And it comes back and it tells me, look at my properties here, or I'm sorry, my process report. And I can see at 7.27, I'm low, it's compared to my 8.025. And, I'm not conforming to the spec I want. So I'm having a problem. Now the question is, am I at 1.5? Am I at 1.25? Am I at 1.48? Maybe at 1.48 it's acceptable. We'll see. But this doesn't give me the answer I want. I had to convert it to a dimensional requirement. So what we did was we made a custom measurement that gives me the ratio of the thread length compared to the pitch diameter. So what I did here was, it's a custom measurement operation. I gave it a name here. It's from the legacy extension set. It comes standard out of the box with the software. I picked the math equation, and what I have is a item from my tree that I use as an input, and then I have an equation. I can put 20 items from my tree. In this case, I'm just simply going to take one measurement. So that's this measurement, thread engagement depth. So that's that measurement right there. I'm going to take that as an input. And then I'm going to come down here and write an equation to say, take that variable, that engagement, and divide it by the pitch diameter. And that will give me the ratio. So it's a simple equation. And once I write that, I have now a lower spec limit of 1.5, which is my 50% additional length. I got an upper spec, just an arbitrary number. Just, I made it the exact same size as the one before, so it looks identical. And if I look at my results, they look very similar. If I look at my process report, I'm getting at 7.27. It's the same numerical value, but right now it's changed my limits to 1.5, and I can see I'm below that, right? So I'm not meeting the spec. I'm at 1.48. Wow, I'm really close. Maybe I can accept this. We'll have a talk about that, or I have to get a longer bolt. So let's show you how I created that. It's a pretty simple thing to create, and we're going to create one from scratch, and what we're going to do is just modify this. We're going to make it a percentage instead of a ratio. So I'm going to add a custom measurement operation. When I go to add that, I can name it what I want. So I want a percent of thread length is greater than the pitch diameter, right? So I want to go get a legacy routine. So I'm going to pick that from my extension set name. And there's a bunch of them in here that I can pick from, some differences, minimum, maximum from a group. There's, a couple here that are very useful. Min and max are very useful. But I'm going to pick my math equation. And what I have to do is start modifying this. So variable x1, I'm going to stand on this measurement here. And I'm going to come over here and put it into my values. I'm grabbing it from the tree. And I'm going to modify that line. So I can put 19 more. I don't need it, but I can make very complex formulas here. So I just have that one variable, and now I'm going to write an equation. And that equation is that same thing I had before. My variable divided by 5.35, which is pitch diameter. And now I'm multiplying it by 100 to get a percentage. So I'm supposed to be at 150%. I can now check to see if that's true. All right, so I'm going to modify that line, and that way it modifies it and saves it in there. I want to change my limits. My lower spec is going to be 150%, and my upper spec is just an arbitrary number, a little large, but I'm just sizing it to make it look just like the other ones. And so now I got all three of them here. When I run my results, I can see where I'm at. I can go to my process report. You can see, I'm at 150 down here for my spec limit. My percentage is 148 to 158, and now I just have to make a decision. But you can see this is a very simple thing to change a measurement into something valuable for the team you're working on. Before, when it said 8.025, nobody knew what that meant, but everybody understands 150% because that's what the spec is related to. So using these types of routines helps you create your models clearly and communicate them clearly. There's all types of math equation functions in there. If we go to the help files and search for the word math functions, you'll find these. Parentheses can be used. All of these, sine, cosine, logs, exponential, square root, change the sign, absolute values, logical operators, all types of things you can use. Just remember, if you use this, it's case sensitive. It's all going to be lowercase. If you type an uppercase on any one of these, like if this was capital SIN, the software doesn't know what it is. So it all has to be lowercase. But this is a cool tool to help report. Multiple cut and paste. A lot of folks don't know how to use this or how to use it properly. And we're going to show you the trick to make sure you click on the buttons correctly if you do use it. So we can copy a single element or multiple elements of the same type. And when we say that, if I'm copying parts, I can only copy parts. If I'm copying holes, I can copy all the holes I want. If I'm copying planes, I can copy all the planes. They got to be the same type, right? And I can, cut them to the same branch in the tree, to a different branch in the tree, and I can copy features or patterns to new mating features. And that's a cool thing here, the new mating features, and I'll talk about that. If you start copying and you use pattern tolerances, they must be of the same type. They all got to be holes, and the pattern tolerance has to be a hole. We'll talk about that. And when you're pasting from a pattern tolerance out to an individual feature, it loses its tolerance. And I'll show you what that means. So here's a note. If you cut and paste features between parts, the datum reference frame is removed when you paste to a different part. It can't guarantee that datum schemes are going to be the same, so it doesn't copy those. It just copies the element, the tolerance. If it was a positional symbol, it'll still say 1 millimeter position. It just won't go back to A, B, and C anymore. So let's take a look at this. So here I have a part, and it's a pretty simple part, and I have some datums defined on it, which are great. And what I want to do is create a pattern tolerance. And when I start creating pattern tolerances, it's a little awkward and not easy to use for putting this pattern of, I think there's 9 holes here. So let's just take a look at this. So I'm going to go to my part here. I'm going to stand on it, right click, and add a feature. And I don't want to add a hole, but I want to add a hole pattern. So here's my pattern. I'm going to pick what it is. So it's going to be a hole pattern, a pin pattern, or a slot. I can never change it once I pick this. I can change the values inside it, but this will always be a hole pattern if that's how I started off and saved it for the first time. So once I have this, I can now go in and start modifying my tolerances. I'm sorry. So I'm going to apply a size tolerance. In this case, I just want a tolerance on the upside of it. I want to do a composite tolerance feature, and I'm going to do true position. For composite, I only got 2 choices. Diameter here, I'm going to 1 millimeter. And I want it to go back to A, B, and C, which is great. And I have those datums all predefined, so they show up in my list, which is great. And then I can create my second note for my composite. And here it's a 1/4 mil, so I want the holes relative to each other with a 1/4 mil, but 1 mil back to the main datums. With the composite, I can't pick from the tree there. They're chosen for me. I got to pick an existing datum scheme from up above or a subset of it. So in this case, I'm just going to pick AB, which is great, and I'm done. So I have what I want, and I create that pattern tolerance. And you can see right now this is 0 because there's no features of size in it. All right, so we want to start defining features of sizes and putting it in there. So lot of folks do it this way, so I'm just going to show it to you. I'm going to add a hole to that assembly, but I got to keep right clicking and going in there. You notice the tab and slots are grayed out. I can't use them. So I'm going to pick a hole because I've already defined that as a hole. And that way it's in there. Another way to do it is actually pick it off of the screen here. And I'm just going to pick it off the screen. And as I pick it off the screen using my hole menu pick, you can see it's adding all 9 of these holes here, but they're outside of the pattern. They're not in the pattern. But that was a lot easier to pick than going right click, pattern, add hole, you know. So we do this all the time. You notice this has a different tolerance for that hole. It has my default tolerance that I have for all new holes being made at this time, which is different than what I have in my pattern. But if I take that hole and I just do a simple cut and I do a simple paste into that, you can see now my pattern has a hole size. It's a pattern of 1, which really isn't a pattern, but it now is taking on that new tolerance. So when I move them from anywhere in my tree into a pattern, it takes on the new tolerance, which is great. It's exactly what I want. So I just created the holes earlier. Now, you know, I can do this one by one, but what I want to do is move all of those in at one time. This is where I want to do copy, cut, paste, delete, multiple features. So what I want to do is start selecting these. And this is the tricky part, is picking the exact feature. You know, what you want to do is pick on the shape of the element. And the key is to pick it down at the, I'm going to say 6 o'clock position of the feature. So right here at 6 o'clock, if I click on it there, you get a check mark. If I hit the control button and I keep going, as long as I hit it at the 6 o'clock position, I will always get that checkbox. If you ever tried and you don't get it successfully, that's why you're not hitting it in the right spot. I found that that works 100% of the time. And I come up here to the top of my tree, and now I can cut those from my tree. And if I go into my pattern, and I can paste them. They all go in there. I'm happy because now I have a 9-hole pattern applying to that tolerance. It does exactly what I want. So that's a simple cut and paste. And you can see now it's 9 times, all 9 show up with that one pattern click. So one of the other things we can do is what we call paste to a mating feature. All right, so I don't have to cut them one at one. I can do multiple, but I can paste them as mating features. And what a mating feature is basically if you had a fixture and you're putting a part on it, if I had a plane there that mates to another plane, it's the exact mating feature. It's the plane that the fixture would have. If I have a hole, it would be a pin. So let's take a look at how this is done. So here's that same assembly. And what I want to do is take this one hole that I have outside of it, down here on the bottom, and go on. So I didn't have it playing. I thought it was going. So, you know, I have a datum A here, and I want to show the normal to that. So you can see it's going down just like I expect it to. And then what I want to do is copy that plane in my fixture. So if I go copy, you see my fixture is empty. I'm going to paste, but I'm going to paste the mating plane feature. I can paste the identical thing or the mating feature. So now I have a feature in there that I'm going to turn everything off and just look at this feature. It looks just like the one I just had. The difference is the normal. The normal is going in the opposite direction. If you know how VSA or VA does assembly logic, when 2 planes touch each other, only the high points touch. So it needs to know the normal direction to do this properly. And so this creates the mating opposing plane, which is the mating feature, which is phenomenal because I can now have that set up in my gauge. All right. So now let's look at a hole. So here I have a hole feature. And if I come up here and I want to put it into my fixture, I want to take this hole and I'm going to copy it. And I'm going to go up to my fixture, I'm sorry, and paste the mating hole feature, a mating pin feature, a mating slot. Because they're all features of size, they have some choices here. But I'm going to create a pin feature. And what it does, it puts it right on the same center line, same diameter, same everything. That's a problem. The pin's the wrong diameter because I want the pin a little smaller than the hole because the hole has a tolerance on it. So let's take a look at that pin and we can change it. But it's the physical pin. I didn't have to go into my gauge and create a pin because a lot of times I have product design, I don't always have fixture design. So this allows me to create my fixture quickly and easily, but I just got to go in there and change that diameter. And I'm going to use like an automotive standard for a locating pin, 150 microns, a little smaller, and away we go. So it makes it nice and simple to create the pin and the hole feature that go together. And it's using this whole cut and paste item. It's a great tool that a lot of folks don't understand. They actually create things from scratch all the time, and it just saves a lot of time and value. Conditional logic. Conditional logic allows us to create conditions to execute or skip any type of assembly routine, whether it's a standard, a kinematic, or whatever. But if you notice, like this cam following here, there's actually, that cam is made up of a bunch of different VSA features. They're different radiuses on different center lines, and I want that cam to follow that. So to do that, I have to use conditional logic. As that cam moves around, it's going to touch different features, and I want that plunger to go up and down based on the feature it's touching, and not just one feature all the time. So let's show you how that works. So I'm going to start off fairly basic here. And in my basic model here, I'm going to have just a block. Oops, I'm sorry about that. Let's try that again. There we go. So here I have a plane, basically a block with a plane on it. And what I want to do is have an element in here that allows me to make this kinematics happen. So I'm going to create a sliding point is what we call it. And in essence, what that is a custom assembly operation. And it's from the legacy set called create slider. And what I'm going to do is be putting some points on. So there's 3 points that I need to have this work. I got to have an endpoint. So if I click on this, you see the endpoint show up where it is in space, right? If I click on the assembly routine for the second point, and my third point, the sliding point, can be anywhere, but I just pick it at the end. But then I want 250 segments between the first point and the second point to be developed. And what it's going to do is make 250 steps that this sliding point is going to slide against. So this is pretty simple. I've got 3 points, and the 1 point is going to move between the other 2. So if I go in here and do my simulations, you can actually see that point move, and it's going 250 steps. So I'm running 250 simulations to get it from one end to the other. And now I'm running it backwards. It reverses once it hits the endpoint. So it's pretty simple. It allows this point to move. Kind of like that cam was rotating. There's a rotational one, but here this is a linear one. And what I want to do is have this point move. And then what I'm going to do is put a pin on here and have it follow it. Excuse me. So to do that, I'm going to take this plane here and I'm going to attach it to the location of that sliding point. So this alignment plane is going to attach to the sliding point, which is kind of cool because now as that point slides around, so does the plane. The plane follows the position of the point. By the way, the point's normal happens to be perpendicular to that plane too, so it follows it perfectly. So now what I want to do is take a pin, and you can see this pin here, and I'm going to take the size variation off of it. And what I want to do here is assemble this in such a way that the pin is going to be tangent to that plane and concentric, as it's touching that plane. I want it to be concentric with, it's repeating the same thing a couple times. How come we're doing that, right? So I want that tangent to be tangent to the plane. Let's make this jump forward a bit. All right, and I want it to be concentric with that moving plane. So as that plane moves, I want the pin to move with it, and I want it to be tangent to that plane. So that's the surface I want it to be tangent to. And we'll run this, and you notice when I do my nominal simulation, when I click this button, it goes to the nominal position. So it's where the plane was and that bar, where they nominally were, but now that condition is being met. It's concentric with the plane and it's tangent, and as that plane moves, the pin moves with it. So the point's moving the plane's moving the cylinder as it goes left and right. So, you know, this is a pretty cool thing because now that I have this movement, I can do other things with it. But, you know, doing it on a straight line is one thing. What happens if I wanted to actually turn down this radius and go down this slope? To do that, I need conditional logic because I need it to mount to that plane, change, and then start going down this radius, and then change, and then be tangent to this later plane. So this is where the conditional logic works. So what I have here is I put a couple of planes here on this little ramp surface. You can see one there and there. That's where they go together. And in addition to that, I've done a couple of measurements, and I need measurements to make this work. So let's just do this first and just show what happens when I make it mate to this plane. And if I show you that routine, I have it tangent to the ramp upper plane, which is great. You notice it's not on the gray part anymore. It's down to the blue part. And it is still coincident with that sliding plane. But if I run this, it's tangent to that plane and it stays tangent to that plane. Nothing is telling it to deviate from that plane. That plane is infinite. So this pin is going to stay tangent to that plane, even though the plane ends, visually, it's mathematically longer. So what I want to do is make a measurement. And that measurement is going to be between this plane and where that upper plane is. And then I do one between this little endpoint and that moving plane. So what I want to do is check if it's on the right here, both values are positive. If it's in the middle, I got one positive and one negative. So anything to the left of that line is negative. Anything to the left of this line is negative for those two measurements. So positives to the right, negatives to the left. And what I want to do is use these to do some if statements. If it's between here and here, and they both are positive, I want to stay in that upper lane. But as it changes, as it goes left and right, these measurements will go from positive to negative, and then I can actually pick which one of these three areas that I want to mate against. And that's what I'm going to use this conditional logic for. So I have that first one. What I want to do is now create a second one that goes to the second angled surface. So I'm going to jump on that one, open it up. I'm going to make it active. I'm sorry. First, let's make it active. And once it's active, now it'll actually work. The difference between this assembly routine and the one before it, it has a question mark on it. As soon as I see that question mark, I know it's conditional logic. Any assembly routine with a question mark has conditional logic with it. So let's look at the properties of this. It's the same alignment plane that's sliding back and forth, but the difference is it's going to that plane down there instead of the first plane that we had. So it's this angled ramp plane that we're using. So all assembly routines, kinematic, custom, regular assembly routines have this tab on top for conditional logic. And in this case, I'm going to say it's active. That means I'm using it. That puts that question mark on my tree. And what I have here is a statement that says if it's past that number, if it's negative, so I got a negative number, if it's less than 0, then I want you to execute this routine. So if it's less than 0, I'm going to execute this, and that's what's going to show up. Now, it's critical in the tree that this shows up after the first one, because this will overwrite that one. But it's nice because anything to the left of that will make it force down to that surface. You know, Now what's unique is, you can see it's after that. This is going to go straight across. It's not going to go down that radius yet, and then it's going to come down that line and over to there. So let's watch this. It's going to go across, go across, go across, down. And it now made that plane. The conditional logic, once that point, that plane was past that dimension, it used different routines to assemble it. So let's look at this one. This is the one for the radius. So here, I wanted to make to the tangent of that big diameter down there. I wanted to make to that radius. And it's only when it's between here. So when it's not either one of the other ones. So this is active. And I have two items in here. So you notice I can pick and or. So the first one is if it is to the right of that first measurement. So if that measurement is to the right, or, so if it's to the right, I don't want to do it. Or if it's to the left of the second measurement. So if it's that measurement's over here, I don't want to do this. The only time I want to do it is when it's in between. So if either one of those ones are true, I'm going to skip it. If they're both false, that means I'm in between. That's what I want to do. So this is kind of unique. Depending on what you pick here in the skip or the execute or above, the greater than or less than will change your values. But in essence here, I'm checking to see if it's not in the front, not in the rear. Thus, it's in between those two. And then I wanted it to execute. But if it's either one of those two are true, I want to skip this routine. So that's what this logic is doing. So let's take a watch this. It goes, hits that point, goes down the radius, right on down, exactly what we want. So this conditional logic allows me to change how the assembly logic is going on, which is really cool. All right. So to show this is really working the way I want it to be, where it's actually touching these tangents, the sequence, of how these things are going together makes all the difference in the world because I got to check the first two. But let's take a look at this pin. And remember, I had a size tolerance on there. I'm going to put a size tolerance of 2 millimeters. I'm going to let this pin grow. So you'll see as this thing goes through its routine here, it's changing size. It's still on center line with that moving plane, but it's always tangent. So this just shows how the kinematic routines are doing exactly what it's supposed to do. Conditional logic, works on all assembly type operations. I can compare this measurement against either a measurement or a value. So I can compare one measurement to another, or I can compare it to a value. I've been typing in 0 as a hard number, but I could compare it to another dimension, right? There's different symbols, equal, less than, these are pretty obvious, not equal to, the exclamation part equals. As long as you know what those values are, you can use this routine. And you can do things like this. This is that linear motion, this great slider routine. It's sliding this slider in and out. And that's extending all this stuff. But here's a create art, and it's giving me a rotational one. So both can be used. And the last thing we're going to talk about today is checking assembly logic. And most common way of checking things is using the model validate function. And I get something like this. It tells me some warning features and all that good stuff. But the big thing it does is it tells you if you meet the requirements to make the routine work. It doesn't tell you if you're assembling the parts the way they are done in the real world. So, that has to be checked too. So let's take a look at this. You notice over here when I do the validation, there's something new in version 12. Suppress warnings for components not assembled to others. These ones down here, remember I had these little lines that I would drive, park, neutral, reverse. They're just in there as placeholders. I don't want to see them. If I check this off and then run my model validate, what I get is everything but those. So I got a lot of warnings here for aligning features aren't right. I can fix those. But in addition to that, we want to make sure it's assembling the way it's supposed to. So here we have that shifter again. And we do this when we check everybody's parts. If I check somebody else's model, one of the first things I do is do the assembly logic and make sure that it's doing exactly what it's supposed to be doing. So let's, take something simple here. We're going to take this pin, and it's a simple little pin that's going into a part, and it's being located on the two ends, and then the shoulder stopping it from going in. Right? So if I look at the assembly routine, we open up the assembly routine, and when we create these things, we're putting them in order. So I got one diameter, a second diameter, and then the tertiary is the translation stop, which is the two surface. It's doing exactly what I expect it to do, which is great. It's locating off the right features. I can see that. And, it makes it nice and simple. One of the things that you want to do is when you create the routines, as soon as you get done creating it, you want to hit the apply button and hit validate. When it validates, it starts telling you if there's any errors or warnings. Here we got a warning. Feature pair 3 is something's wrong with it, right? And let's take a look at those. So I'm going to turn, excuse me, sore throat here. I'm going to turn all my parts off. And if I look at that, the normals for both these planes are going in the same direction. And when I assemble things, typically I want those planes going in opposite directions to mimic real life. So let's take a look at what we got. And I can see there's my pin inside my other part. And it looks like the normal for my pin's going in the wrong direction. It should be going down the shaft versus away from it. So I need to go in there and fix that, which this helps me figure that out. So we do these things to make sure we're doing it correctly and to validate things are working in the direction that they should go. All right. So, excuse me. So here's my assembly logic. I can just stand on them. And when I stand on it, I can see what's going on instead of going through them one by one. And so here I got a couple of parts. What are these two flanges up here? I'm not sure. I want to show my part. In this case, I have this part. And I'm looking at it and going, well, that's on the inboard edge. How does that locate well, especially me checking it? I don't know all my systems. So how is it pivoting off this bottom piece and then resting on those two surfaces? Well, let's take a look. So here we have this core assembly. It's going to the adapter plate and the base pin, which was what I just stood on. And I can see that by my notes and how well I described it. And I'm just going to stand on these real quick. It's going to go off of that axis. It's going to pivot off of that, which is great. It's going to pivot off that little axis, which are concentric. And then these two surfaces. And basically, I'm going to rotate up to that and stop. And then this is going to stop translation. It's going to be between those two planes, which is great. So now that I have these features defined, I know what's going on. I just need to understand what those two planes are on top because it just didn't look to me right. So if I show my part, I can see that's on the inside, but I know my other part's on the back side. How is that working? So I'm going to hide these parts and show my other part that mates to it. And this one takes a second, a little bit more. Oops, there we go. Yep, there it is. So what's going on here? How does this work? Oh, I see what's going on. It's like a little snap feature. I rotate that in and snap it in. That makes sense. I couldn't figure out why it's on the back side. But we look at these things and visualize to make sure we're doing exactly what the assembly process shows us and is identical to. So we want to make sure it mimics real life and is functionally correct. So last question, a couple more minutes and we're done here. But do you ever come across errors in your assembly logic?
Looks like we had a pretty close one between
Nice.
Sometimes, but there.
Yeah, it's it's a large mix, but there's usually some types of errors. I would say there's 2 or 3 of us that are very experienced modelers at our location, and it's very rare that we make a model off the gate the first time that's perfect. We internally check them ourselves first, and I usually always find some little bug or error, and and every now and then we've reported it, and as soon as we get done reporting it, we find another bug, and we then have to change our reports, which is kind of time consuming. So it happens. Checking it and having an independent person check it is the best way we've ever found to solve all these problems. So that kind of talks through the 7 habits. I got one extra tip. If you don't use the ribbon bar, you've noticed I've been using this ribbon bar in my models. If you don't have it, version 12, I believe it's now defaulted to be on, but in prior versions, version 9 on up, I believe it is, if you go to your system properties and go into your environmental variables, and you type this in, tcvis_enable_ribbons, you call it true as an environment variable and add that, this will show up the next time you launch VSA. So you get rid of the old menu bar, and now you have the new ribbon style, and it's a quick thing to do. So with that, this is all about sharing ideas, and that's wrapping this up.